next presenter, Greta. I enjoyed having Greta in the group quite a lot. She has a mind for mechanisms in physics that is really really impressed me, and I don't say that about a lot of people very often. So I was kind of that, and some of the communications about some of the stuff that we did that was more policy and society related. For example, the capitalism versus climate. We had a discussion here about capitalism and climate, and Greta's commentary on some of that was just, I don't know, it's just a sophisticated student that I'm really interested to see how this career is evolving, and participating in a project understanding the effects of prescribed burns on weather and radiative forcing of 2025 California case studies was just really, I learned a lot, and I think you'll all be very impressed with this. So Greta, the floor is yours.
Okay, thank you. Yeah, thanks. All the bottom are one. All right. Hi, everyone. Good afternoon. My name is Greta Davis, and for the last couple of months, I have been looking at the effects of prescribed burns in California on radiative forcing and weather. Let's get started. Wildfires are, summer wildfire season in California is expected to increase due to climate change. California is a region that is experiencing increased vapor pressure deficit as a consequence of climate change, which is an absolute difference between the atmospheric vapor pressure and the saturation vapor pressure at that temperature, which causes fuels to dry out faster when there is a higher vapor pressure deficit, and it is an important wildfire prediction metric. Prescribed burns emerge as a really profound solution to wildfire. California has a rich history of operating prescribed burns, which has caused many California ecosystems to be fire resilient, and in fact several are fire adapted, meaning they require fire for ecological main state functioning. And prescribed burns have been shown to be very effective in reducing the severity of wildfires when they do occur. There are some barriers to implementing these prescribed burns, including fire weather. If it's too hot or too windy to operate a prescribed fire, there are chances that it may escape into undesired regions. And fire weather or prescribed burn windows that are acceptable weather opportunities have been shrinking in response to climate change. There are also national ambient air quality standards, which, especially in a state like California with major population centers that are releasing lots of pollution, is of high concern and is a prominent barrier in implementing prescribed burns, especially in urban areas. And there are also organizational barriers related to the difficulty of getting equipment or getting a professional to parameterize the burn and submit a smoke management plan to the air district that has to approve it. We know that smoke will have a radiative effect based on just basic mechanistic principles. When we have a layer of aerosols in the atmosphere, smoke will perform both absorbing and scattering effects of short and long wave radiation, which makes it a very complicated problem to look at in general. But essentially, when shortwave solar is coming in from the sky, aerosol layer will reflect it and also absorb some of that light, transferring it into kinetic energy and causing warming within the layer where the aerosol is. As we increase our use of prescribed burns as a forestry management practice, it would be interesting to look into how the plumes might affect radiative forcing at the surface, and there are interesting experimental routes that I'll get into later. But first, let's just look at observing these things. So what I did is I got fires, any fire that was operated within my study time frame that was larger than 50 acres, I collected, and from the CAL FIRE website, which provides daily information about where fires are occurring, just as like a public service that they do. And I parameterized those fires in Blue Sky Playground, which is a modeling software that is open source and provided by the US Forest Service. Essentially what you do is you put in information about the fire, like its latitude and longitude and the acreage that you plan to burn. And this model will tell you what type of topography exists there. There are meteorological conditions that are paired to this. And it will populate a plume dispersal based on the initial conditions that you set for your fire. So here is an example of what a blue sky dispersion looks like. This video depicts a modeled plume dispersal from a prescribed fire operated in Dog Valley, California, which is part of the Tahoe National Forest. You can see the plume disperse eastward over the Reno-Sparks area and southeast into Carson City, dissipating before it really reaches Fallon, Nevada. Keep this video in mind because it will be relevant to one of our case studies in just a minute. From here, once I had an idea of where the smoke plume dispersed, I got weather and irradiance data from a company called Solcast. Solcast produces a data product for people interested in setting up solar PV farms, which is especially relevant to this project because when we're considering the scattering effect of the smoke aerosols in the atmosphere, the level of solar radiation that is received at the ground, which is an important parameter for solar people as well as for aerosol studying people. So that is what I used. I was looking at this Solcast data and confirmed it against a ground-based sensor from the NOAA SOLRAD program, which is an array of ground-based sensors that is receiving solar radiation at the surface, actual values. This SOLRAD sensor is receiving point-specific changes in cloud cover, whereas the SOLRAD data is sort of interpolating the changes over both time and space, which is under cloudy conditions causes it to be slightly less, doesn't capture the extremes that the ground-based sensor does. So for this project, I looked mostly at clear sky conditions, which as you can see on the left, the Solcast data does a much better job of capturing that curve. Our first case study is for the video that we watched earlier. These curves are the same curve from the previous slide, just a daily incident radiation at the surface. Those top yellow and orange curves show the in-plume and out-of-plume direct normal irradiance. And to make these more clear, I have tracked the daily peak direct normal irradiance in these cities. We find that Fallon, outside of the plume dispersal perimeter, experiences a much slower decline in DNI relative to the in-plume cities. This was notably a burn that occurred over the course of 4 days, so the smoke inventory was accumulating in these cities for a while. And we do see that the increased smoke inventory in the atmospheric column causes that enhanced attenuation of light. Notably, Fallon has a lower direct normal irradiance than the other cities just as a base state because Fallon is located at a lower elevation, which means it has just more atmospheric column above it in general for the light to be attenuated through. The temperature effects notably don't seem to rely on transient smoke presence as much as the direct normal irradiance does, which makes sense. Temperature will tend to be controlled by trends that are much more powerful than transient smoke. This is an additional case study. The video is going to play in a second. As we can see, the smoke for this fire spreads southeast into Ukiah and Clear Lake. And here, the video is going to stop, but what essentially happens is this particular video was a modeled run of 30 hours, so starting the day that the burn starts and then continuing until 6 a.m. the next morning. If we were to continue seeing the rest of the day on May 17th, we may presume to see that the smoke stays in the valley region. And we can see the time-locked effect of this. So on the 16th, we can see that the direct normal irradiance for all three locations dips slightly. But on the 17th, when the smoke persists only in the valley region, we see that the direct normal irradiance dips there and not in the other nearby zones where the smoke has already dissipated, which is very interesting. Indeed, in most of our prescribed fire cases, we found that the plume caused a reduction in direct normal irradiance at the surface. But there are many ways in which smoke can interact with the climate system, and this is just really barely scratching the surface. Smoke can modify weather systems by a number of mechanisms. First of all, fires release greenhouse gases in addition to the aerosol particles that they produce, so the greenhouse gas contribution will have some effect. There's the aerosol direct radiative effect, which this project has been focusing on. There are also indirect effects related to how aerosols act as cloud condensation nuclei, which will increase the droplet number, the number of droplets in a cloud, essentially, while decreasing the size of those droplets because the particles give solid surfaces on which water molecules can condense. And having an increased number of droplets while smaller droplet size will tend to reduce the likelihood of collision and coalescence processes that cause clouds to rain out, which will make the cloud lifetime higher and also make the cloud optically thicker to incoming solar, so much more reflective clouds when you have smoke infiltrating them. But with a majorly cloudless land surface like California, observing these cloud brightening effects overland is damn near impossible. Fires also induce local circulation change. This is more observable for actual wildfires than prescribed burns because there's a much lower heat input for prescribed burns, which makes the smoke less thermodynamically inclined to rise and disturb the mean state. Smoke can also darken snowpack and cause increased melt rates and cause albedo effects with respect to the ground surface. It can fertilize phytoplankton populations, which can have all sorts of effects, and reduce vegetative cover, which will increase dust aerosol flux and cause some sort of surface albedo change. These processes are really varied and complex, and it would be interesting to know more about them. I think that prescribed burns offer an interesting experimental route toward marine cloud brightening, which is the idea that we might be able to reflect incoming solar very efficiently over marine areas because the ocean is quite a dark blue color. We can see in this image on the left. The ocean is quite a dark blue color, whereas marine clouds are very white and reflective to incoming solar. So by having less light enter our atmosphere in the first place, we can counteract the greenhouse gas effect. And prescribed burns do not currently operate as like a solar geoengineering strategy, but there are studies done on the effect of wildfire on marine cloud brightening, which have shown pretty substantial increase in marine cloud fraction, or the amount of ocean that is covered in these thick white clouds, which causes pretty significant sea surface cooling and could be an interesting route. So I propose experimental burning in Humboldt County, which can be compared to the results from this study, which is looking at the 2020 Western US wildfires. So you can get a little bit of that comparison element. Humboldt County also has elevated terrain. So I mentioned earlier, smoke from prescribed fires sometimes doesn't always get up into the upper tropospheric levels. And if you're operating it at a higher elevation, it would already be there. And it's also right next to the ocean, which lends itself well to that. Oh, and Humboldt County is north coast California, which is not a terrain type that's characterized by like shrubby coastal chaparral, which is more responsive to prescribed fire than like Southern California ecosystems tend to be. Yeah. So we can observe the direct radiative effect of smoke plumes from prescribed fires. Any results from this presentation are entirely preliminary, but interesting nonetheless. The DNI influence is mostly based on transient smoke presence, so if it advects out of the region, those trends won't be observed. The cooling temperature effect that is observed for wildfire smoke that is lofted up into the atmosphere is not observed for prescribed fires, and that could be because the smoke is at the ground level where it's causing a local heating, as opposed to being aloft where it's mostly impacting the climate based on its scattering. And smoke cloud interactions are hard to measure, but they would be easier to measure over ocean, so I think that we should do that. And there is potential for future research because prescribed burns, we know where to put them, or we know that we can put them where we want them. We can have increased specificity with modeled reanalysis of prescribed fires as opposed to wildfires, which is interesting and good. I think we should do it. I'd like to thank Corey, my committee chair, and Dr. Luca Carmignani, who helped me with this project. I'd also like to thank the U.S. Forest Service for producing the Blue Sky model, Solcast for providing my data, also CAL FIRE for providing my data, and SIO, my friends, my cohort, my family for helping me through every stage of this process. I'll now field questions.
This was a great presentation, Greta. You mentioned dust on snow, and this was something that I came across in my research, and I was wondering, like, how seriously, if you know, like, what is the state of California investing into, like, looking at this more, especially as, like, wildfire frequency is increasing, or prescribed burns might need to increase with climate effects? There was a question there, I think. Yeah.
So, wait, was it connected to the snow?
Yeah, no, you said there was like a dust on snow effect, and I was just wondering, like, do you know from prescribed burns, like dust that's being produced or ash, like if that's being considered seriously by like CAL FIRE, state of California agencies, like at all?
I would say, like, almost certainly not.
Oh.
Is it being considered at all? Generally, smoke from prescribed fires is only studied within the context of how it affects human health. Yeah, not so much on the physical radiative impacts.